So one thing I did want to point out from our trigonometric functions, because obviously you can see these are written as ratios. Now with our idea of taking that number line and wrapping it around the unit circle, if we go with that, then we're saying again, our t would be the real number, and x and y would be the point that would correspond to a point on the unit circle with that value of t. So based on that, we define our sine of t as y, cosine of t as x, and then the tangent becomes y over x, or basically it's going to be the ratio of sine over cosine, right? Because remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent comes out to be opposite over adjacent. So opposite coming from the sine, adjacent coming from the cosine. So as you can see, since our x is going to be in the denominator, any value in the denominator cannot equal 0. So anytime you end up at an ordered pair where your x value is going to be 0, you're actually going to get an undefined value for your tangent function. And actually that same thing is going to happen right here for secant, because secant is the reciprocal of the cosine function, so that x will become 1 over x, right? And again, x cannot be 0. So at the same point where your tangent function is not defined, your secant function will also be undefined. Same thing's going to happen here with cosecant and the cotangent functions, because any value that has a y equal to 0 is again going to be undefined. And you can kind of see, I've put a couple examples here. So at the 90-degree angle where you have t equals pi halves is going to be right here, right on our y-axis at the point 0, 1. So you can see our x value is going to be 0 here. So this would be the instance of where tangent of pi over 2 and secant of pi over 2 are going to be undefined. So you guys should actually be able to verify that in your calculators. Just go ahead, take your tangent function, type in pi over 2 for the tangent function, and see what your calculators are telling you. Now in my calculator, I need to do the tangent key first and then type in pi halves. With some other calculators, you have to type the pi halves first and then hit the tangent key. So just kind of see what your calculator lets you do. And for pi over 2, you need to make sure, if you're getting a value, make sure your mode is in radian mode.
Yeah, no, this is error.
In radian mode, you should get an error, right? Because pi over 2 would be in radian. If you leave it as degree mode, then it's actually taking the value of like 1 point something in that. And this is something, remember, I had talked to you guys about. Make sure you keep your calculator in correct modes, because we will need to often change it back and forth between degree and radians. Now, how would you go about calculating the secant function on your calculator? Do we know that? Secant is the inverse for which function, or the reciprocal for which function? Cosine. So you will see above the cosine key, you should see the cosine with that inverse notation. So you'll need to do that to check for your secant function. Right?
Secant of what?
Secant of pi halves. Here. Yeah, so for that cosine inverse, which is technically not an inverse function, but that's how the calculators put it, you should also see an error message. And obviously, same thing's going to happen for our cotangent and cosecant functions when y is equal to 0, and we know y is equal to 0 right here at the point 1, 0, or at the, or basically your x-intercepts -1, 0. So same thing if you try to type in cosine of, not cosine, cosecant of 0, cotangent of 0, you should get an error message. For that matter, even for pi, you should get an error message. And those would again be those inverse functions on your calculator. We talked about the dividing our circle into equal parts. I think we had done the 4 and the 8 equal parts, so you kind of have that. But I kind of like this. Your textbook actually also does the 12 equal parts, and then it's showing you what those corresponding ordered pairs are going to be for all of those, excuse me, for all of those points. So let's take a look at just some simple ways of how we're coming up with these points. So we're actually referring to this diagram over here, and we're talking about this line right here. Okay, this is the line y equals x. Basically, it's passing through the origin with a slope of 1. So the idea here is this is a point on the line y equals x. If I put this back into our unit circle formula, if y equals x, I can replace my y squared with x squared. Adding this up together gives us 2x squared. Isolate that x squared by itself, and when I take a square root, I will end up with square root of 1/2, and then we're rationalizing our denominator, which is what cleans it up into plus or minus square root of 2/2. And they're saying, okay, so this is how we can basically come up with what our ordered pair for that point should look like when we are at, you know, at this point right here, which, do you remember what that angle comes out to be?
Is it 4 or pi over 4?
Yeah, it's going to be pi over 4. Yeah, so this is going to be basically what that ordered pair should correspond to. So the idea is we should be able to kind of use this idea of different geometric and algebraic functions that we have looked at to come up with these kind of ordered pairs for our different angles. And, you know, of course, you can try and verify this for all these squares that we have in here. Before actually looking at example 1, I would like to go and look at this second supplement that I gave, which is for the Foundations of Trigonometry. Yeah.
I mean, it wouldn't be pi over 4 because it needs to be an ordered pair.
No, the angle would be, your central angle would be pi over 4, right? It's the ordered pair that's corresponding to that angle. Okay? Okay, so this handout. So just to kind of help us again come up with how can we calculate these sine and cosine values other than using the opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent formulas that we did for sine, cosine, and tangent. You can use the right triangle trigonometry. You can, of course, use the idea of algebra to help us out. But the other tool that I want to look at is actually the reference angle concept. So the idea with the reference angle here is, you can kind of read that paragraph here if you would like to. But the idea here is, let's say this is my initial side right here. My terminal side is ending right over here, and this angle is going to be 5 pi over 6. Now I need to figure out what this coordinate pair is going to be for the point on the unit circle, that x and y value. So the idea here is, if I'm going 5 pi over 6 all the way to quadrant 2, then right before I get to that half semicircle or half a revolution, the side from here to our terminal side, this angle is going to be pi over 6, right? Because remember, they have to add up to a total of pi. So this angle here is going to be pi over 6. So we can use the idea of pi over 6. If I put this in the standard position, and you can see that in your second figure, if I just do this little reflection over here, this ordered pair is going to be easy for us to calculate, which comes out to be 3 pi over 2 and 1/2. So the idea is I can actually take this, reflect it onto the quadrant 2 side, basically with respect to the y-axis, and I can actually get the points for our central angle of 5 pi over 6 by using this idea of reference angles. And the only difference it's going to be is I'll need to change my signs based on the quadrant it's going to be in. So if I'm reflecting it from quadrant 1 to quadrant 2, I know my x values become negative. If I actually take that same angle and reflect it with respect to the x-axis down into quadrant 4, how are these signs going to change?
X stays positive and y goes negative.
Yeah, y goes negative. So that's the idea. What we do with reference angles is if you can do the basic angles and you can actually use these idea of reference angles for something that may not be a very common number that we're used to, and still be able to come up with what those values of sine and cosine, or basically our ordered pair of x and y, is going to be. So this one here just kind of gets into a little bit more description of what I just talked about, which is depending on which quadrant you're going to be, you're going to need to change the signs for your ordered pairs. And again, we're using this idea of symmetry because think about it, you do have symmetry in a unit circle. If you fold along the y-axis, your two semicircles left and right are going to be exactly the same. If you fold along the x-axis, then your top and bottom semicircles are going to be the same. So that really helps us when we're trying to figure out what these sine and cosine values are going to be. So they actually get into a little bit more detailed descriptions here. I'll leave that for you guys to just kind of read through. But this table here is really going to come in handy for us because these are going to be some of the main angles that kind of keep popping up every time we do these calculations. So 0 degrees we know is right at that starting point. So in radians, that's going to be, again, 0 radians in terms of angles. That corresponds to that ordered pair of this point right here, which would be the 1, 0. So that's going to be an easy one. 90 degrees, we know that's going to be at the y-intercept on the positive side. So that's going to be the ordered pair 0, 1. So that can help us come up with our sine and cosine values. And then your 30, 45, and 60 degrees are, of course, going to be, just 3 different sections if you make it through here. And those are probably the ones that we definitely want to get comfortable with. So 30 degrees in radians is going to be pi over 6, square root of 3 over 2 for the cosine, 1/2 for the sine. 45 degrees, they are the same values for both cosine and sine. So you've got square root of 2 over 2, square root of 2 over 2. And then 60 degrees is actually switching those sine and cosine values, right? So now cosine becomes 1/2, sine becomes square root of 3 over 2. So these 5 are probably going to be what we really need to kind of hold on to. If we can remember those using the idea of reference angles, you can see we can come up with all of these different angle measurements. You've got theta equals 225 degrees. So we know 225 degrees is basically going to fall into third quadrant, right? Because this one goes to 270 starting at 180. So what you can see here we're doing is we're taking our measurement of 225, subtracting 180 degrees from it, and that's giving us a 45-degree angle. So think about it. If I'm subtracting 180, this is my initial side going all the way, this is my terminal side. If I'm subtracting 180, which means I'm taking this whole part out basically, think about this side being your initial and we're going down to 45 degrees, right? Which means, again, I can use that idea of reference angles to help us out and calculate what our sine and cosine is going to be. So this is a quadrant 3 angle. We know both x and y, or both cosine and sine values, are going to be negative. This is coming from a 45-degree angle, so it's both square root of 2 over 2, and now you're just putting a negative sign on that. And you can kind of see with these radian examples, so let's look at 11 pi over 6. 11 pi over 6 is actually going to be, as you can see, it's going full revolution here. So we can do 2 pi minus theta because it's going to be right here in quadrant 4. So we're taking 2 pi minus theta, which will just give us this little portion. And that comes out to be pi over 6, which is, of course, our 30-degree measurement. So that's going to be your square root of 3 over 2 and negative 1/2 because you're in quadrant 4. So I'm not going to go through all the examples, but I do want you to understand that the use of reference angles, if you can subtract 180 degrees from it, if you can subtract, sometimes, if it's greater than 360 degrees, then you want to take that full revolution out. If it's a quadrant 4 angle like we had here, then it's actually easier to take 2 pi minus that angle and get whatever your remaining value is. So a lot of different ways of doing this. So basically, if you're a quadrant 3 angle, you want to subtract pi or 180 from it. If it's a quadrant 4 angle, you want to subtract the angle from 2 pi. So some of these techniques, we'll kind of look through as we go through examples over here. And this is just, again, another unit circle here, which I have already given you guys a copy of this. All right, so let's go back to our handout and see how we can use these ideas of reference angles and right triangle trigonometry to help us come up with these values. So we are asking basically to figure out what the 6 trigonometric functions will be for each of these real numbers. So we're starting out with pi over 6. Now pi over 6 obviously is the 30-degree angle. So you can use that table as I was talking about. But let's say, right now we don't have that table memorized. We don't know how to come up with this value. So we can actually use the idea of the 30, 60, 90 degree triangle. And this is going to be another tool which is really going to come in handy, especially if you are having trouble remembering what's the cosine of 30 degrees, what's the sine of 60 degrees. So this triangle will really help you out in that case also. So the 30, 60, 90 degree triangle, the ratio for the sides is going to be, the shortest side is going to be 1 unit. The second side is going to actually be square root of 3, and the hypotenuse is going to be 2. Now think about what is the approximate value of square root of 3?
1.5.
It's actually 1.7, but yeah, even if you think 1.5, square root of 3 is going to fall between 1 and 2, right? So technically, this is incorrect when you write it as 1 to 2 to square root of 3, because it should actually be in this order, 1 square root of 3 to 2, if you're aligning it with these angles of 30, 60, and 90, but it's easier to remember 1, 2, and 3, right? So that's kind of why they switched that order. But the side opposite to 30 degrees is going to be the shortest one, so that's 1. The 90 degrees, the largest angle, which means the side opposite to it would be the longest side, which will be your 2. And then, of course, across from 60 degrees is going to be square root of 3. So this is where I'm saying this triangle will really come in handy if you remember those ratios, because then you can use the SOHCAHTOA concept to help you come up with the ratios for your sine, cosine, and tangent. So sine we know is opposite over hypotenuse. So with respect to 30 degrees, that's opposite, which is side 1. Hypotenuse is 2, and that ratio comes out to be 1/2. If we're talking about cosine, again, with respect to 30 degrees would be adjacent over hypotenuse. So that's where the square root of 3 over 2 is coming from, which of course, if you had to do tangent for the 30-degree angle, what would the tangent be for this?
1 over square root.
Sorry?
1 over square root of 3.
Yeah, 1 over square root of 3, and then you'd basically just need to rationalize your denominator. So using this idea, you can see if we come up with our 3 main functions, the 1 over square root of 3, of course, after rationalizing will become square root of 3 over 3. Then you're literally just inverting these values to get your other 6 functions. So sine, the reciprocal is cosecant, 1/2 will become 2 over 1 or 2. For cosine, the reciprocal is secant, so square root of 3 over 2 will become 2 over square root of 3. Rationalize that, which gives you the 2 square root of 3 over 3. Tangent, 1 over square root of 3 or square root of 3 over 3. For cotangent, again, you're basically, if you just actually invert that, you get your square root of 3 for the cotangent function. So lots of different ways to come up with these angles, reference angles, 30, 60, 90 degree triangle, or using SOHCAHTOA concept also to help you out. Okay, now let's see how we can do a different example. Here our t value is given as 5 pi over 4. So 5 pi over 4, of course, falls into quadrant 3. And what I do a lot of times, if I can't remember what quadrant that's going to fall into, convert it to degrees, so at least you get an idea of what quadrant you're looking at. So again, we know we're starting at 0 degrees, 90 degrees, 180, 270, and 360. So if converting it into degrees help you figure out what quadrant you're going to be, go ahead and do that. We subtract 180 from that. Remember what I said, if it's in quadrant 3, subtract 180 from your measurement, 45 degrees. And then again, we're using the idea of either the table, or you can actually use the concept of an isosceles triangle, kind of like the 30, 60, 90, but this one is basically 45, 45, and 90, right? So since my angle measurements are the same for both of these acute angles, these two are going to be the same measurement, which is the definition of isosceles, right? The two sides are going to have the same length. So this is going to be the ratio of 1 to 1 to square root of 2. So again, using our Secant, you can come up with your sine and cosine values, which is where our square root of 2 over 2 comes in. We know these guys are quadrant 3, so they're both going to be negative numbers. Okay, and then of course we have our 6 different functions based on that. This one is talking about your angle pi. So of course that's going to be the negative x-intercept. That's where you're coming with your -1 and 0 from. Obviously some of these functions will end up being undefined just because you do have a 0 in your denominator. And just kind of quickly going over negative pi over 3, of course, being a negative angle, we are looking at quadrant 4. If it was positive pi over 3, you would be in quadrant 1. And then again, using the idea of the 30, 60, 90 degree triangle, we're coming up with our values here. So you can kind of look through that, but I would like us to practice. Obviously, I've hopefully given you ample space here to work through these examples. So let's take a look at example 1 here. All right, so they're telling us so that's a fairly simple angle. What would you do for pi halves?
It's 90 degrees.
Yeah, it's 90 degrees. So what would that put us at?
0.
So we're talking about this point right here, right? At pi halves. So this would be our ordered pair of
0,
0, 1. So what would you say is sine of pi halves now? Because remember, we're asked to evaluate all 6 functions.
So that's just x, right? Just 0.
Okay, go back a couple pages and see how did we define our trigonometric functions in terms of x and y. I think it may be a page or 2 back.
It's just y.
Right. Because remember what I told you, think of alphabetical order. So if we're doing this as x, y, in terms of sine and cosine, c is obviously going to fall before s. So it's actually cosine for x, sine for y. So just remember alphabetical order, and hopefully that'll help you say that c goes before s. So sine is, of course, going to be 1. So what do you think will be cosine?
0.
0, very good. tangent.
Would that be does not exist because it's sine with cosine?
Yeah, because it's going to be opposite over adjacent.
Or
No,
it's
it will
undefined,
not be.
is that what it's saying?
It's going to be undefined, yeah. Because tangent is always going to be sine over cosine, or you can think of it as opposite over adjacent, whichever helps you out. We know sine is 1, cosine is 0, which of course comes out to be undefined. Now, based on that, what would those other 3 functions look like? So sine starts with an S, its reciprocal will be cosecant. Very good, cosecant. Of course, for cosine, it goes with secant. Tangent goes with cotangent. So if sine is 1, what is cosecant? 1 over 1, right? Yeah, so basically, cosecant will also come out to be 1. Secant?
Undefined.
Yeah, because remember, again, if you go back and look at the page I was talking about, you kind of use that idea, or basically use the idea of inverting your fractions. This little box over here. So that means you're technically doing 1 over 0, right? For secant. Because if I take the inverse of this fraction here, it's going to come out to be undefined. What will happen with cotangent?
It'll be 0.
Yeah, because if you invert this fraction here, 1 over 0, it will become 0 over 1, which ends up becoming 0. So just because tangent is undefined doesn't mean cotangent will be undefined. And again, just to remind you, so sine will equal the y coordinate, cosine equals the x coordinate, tangent comes out to be y over x, cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. Questions on this first example? Okay. Okay, t equals 0. Where is that going to be?
1 comma 0.
So 0 means you're right at that initial side, right? So that is going to be the order pair 1 comma 0. So again, remember cosine is the first order, sine is the second order. Okay, go ahead.
Cosine is 0, right? Or sine?
No, sine will be 0.
Sine is 0.
Yeah. So what will be cosine?
1.
1. Very good. Tangent.
0.
0 over 1.
Yeah, 0 over 1.
Yeah.
And then sine will be with cosecant. Secant goes with cosine. Cotangent with tangent. So what are we looking at for cosecant?
Undefined.
Undefined, yeah, because you're going to end up with basically 1 over 0, right? Okay, secant.
1.
Yeah, because this is actually going to be 1 over 1. It's gonna be 1, 1. And cotangent. Yeah, because you're doing 1 over 0. So remember, if there's no denominator, 1 is always a denominator.
So for like secant, it's just the y value over y value.
Secant is 1 over.
1 over 1.
Hold on. So again, if you look at page 2 of your handout from 1.2, secant is going to be 1 over x. So you basically, if this guy is y, then you're taking 1 over y for this one. If cosine is x, you're taking 1 over x for secant. And then tangent, of course, is y over x, which becomes x over y for cotangent. Anybody else have question on that part B? Okay, how about I give you guys a couple minutes, try and see what you can do for parts C and D, and then we'll discuss it together. That's what we're doing here. So like I said, if it helps you, you can think about converting your radians into degrees, which basically would be 180 divided by pi, right? If you're going into degrees, so this is where your pi would cancel out. 6 goes into 180 positive 3 times, and then that will give you negative 150 degrees, right? Which tells us our reference angle here is going to be 30 degrees, or basically pi over 6, or negative pi over 6 in this case. Okay, so our reference angle yeah, the 150 subtracted it from 180. So this should be theta, which would be equal to 30 degrees. But yeah, basically that's what we're doing. 180 degrees minus the 150 to get 30 degrees. Okay. Now, as I was telling you, since we know these are quadrant 3 angles, both our x and y values have to be negative. So that's one thing we want to keep in mind. And then using our uh, 30, 60, 90 degree triangle, this will be our 90 degrees. Of course, this guy here is going to be the 30 degrees. Let me see if I can make him bigger. So 30, 60. Now remember, the shortest side will be across from 30 degrees. So this is going to be 1. The longest one is the hypotenuse, so that's going to be 2, which makes across from 60 our square root of 3. Now we're talking in terms of respect to the 30 degree angle as our reference angle, right? So that means if I'm talking about sine of negative 5 pi over 6 in terms of the reference angle, you're looking at sine of negative pi over 6, which again is the 30 degree angle. That's going to be opposite over hypotenuse, right? Which is going to be the 1/2, but being a quadrant 3 angle, you want to put the negative sign in there, okay? For cosine, again, our original angle is negative 5 pi over 6. Reference angle is negative pi over 6. Cosine, again, with respect to the 30 degrees, is going to be adjacent over hypotenuse. So that's your square root of 3 over 2. Again, quadrant 3 angle, which makes it negative. Okay?
So I got, so subject to use sign, so it's 1/2, so how'd you get to negative?
So the negative is coming from the fact that your original angle, -5 pi/6, is in quadrant 3, so we know all the values in quadrant 3 are negative. So that's where we're using that from.
On the test, if we have a problem like this and we have the unit circle memorized, do you still want us to show the work?
If it's memorized, then it's fine.
Okay.
But then make a note that that's what you are doing.
Okay.
Because if you don't, then this would kind of be your route to
Okay.
go. Okay? And like I said, you also have that table I showed you in your supplement. So you can memorize that table also, which can help you. So yeah, either one of those. So if you know the sine and cosine, what does the tangent come out to be? Go ahead.
1/2 over.
So basically you're taking the ratio of those two values. So sine goes on the top, cosine on the bottom, and then when you clean it up, what will it become?
2 times the square root of 3 over 6.
Okay. Let me see if I can just make that bigger. All right, so you're basically taking -1/2. Remember, when you're dividing two fractions, you can invert the bottom one and make division into multiplication. So your two negatives will end up becoming positive. 2 and 2 will cancel out, giving us positive 1/√3. Rationalize your denominator. This is what you should end up with. And anytime you are using radicals in your sine and cosine values, it's a good chance you may have to rationalize your denominators. Okay, now based on these 6 functions, what will their reciprocal functions look like? Very good, yeah. Okay, secant. Okay, so after you rationalize, what will that become?
2√3 over
2 square root 3 over 2.
Yeah, so you're just again multiplying by square root of 3 numerator and denominator. It will become -2 square root of 3 over 3. Very nice. And last one will be cotangent. So actually, what you can do for your tangent is we had 1 over square root of 3, right? Before we rationalized it. So if you just invert that, you would actually not have to worry about cleaning your fraction up. So you can do square root of 3 over 1 and get square root of 3 of your answer. But let's say you don't think about that and you're still using this guy. So if you needed to do that, okay, so let's say you are looking at inverse of 3 over square root of 3. You use this instead. You will need to rationalize the denominator for this guy then, which will end up giving you 3 square root of 3 over 3. Yeah, take the 3 and 3 out, and you can get to your answer that way also. So if you want to avoid having to do that rationalizing, then you can just go with 1 over square root of 3 and use that to help you out. Okay. All right, questions on part C. Okay. Do you have something for part D? T equals -3 pi over 4.
2 over 2 and negative 2 over 2.
Okay. What quadrant does this angle fall into?
The 41. No, wait.
2 and 1. Yes.
It will not be quadrant 2, no. Because it's negative, right? Which means you are going clockwise. So what quadrant does it fall into?
Yeah. 4 quadrant. Oh, third quadrant.
Third quadrant.
What?
That's a negative.
What is negative 3 pi over 4 in degrees? Oh, if we're converting this into degrees, of course, these guys cancel out. So let's see, negative 3 times 180 divided by 4. Yep. Negative 135 degrees. So it's going to be third quarter because it's more than 90 degrees. Again, third quarter means both our numbers have to be negatives again. So what's our reference angle then?
So I think you go clockwise.
45.
Say that
I
one
think
more
you
time.
go counterclockwise.
Counterclockwise is positive, clockwise is negative.
Oh,
Negative 45 degrees.
Yeah, so your reference angle is coming out to be 45 degrees. So this is where, again, you can use the idea of that isosceles triangle, right? So if you use the isosceles triangle, and this would be 90 degrees here, 45 and 45
so
here.
the isosceles were negative?
Oh, isosceles can work for positives and negatives. I mean, your
So-
triangles will work for any
So
of
it's
them.
just using different values instead of 30, 60, 90, you get 45.
45 and 45. And then remember, since your angle measurements are the same, the two legs will also be the same measurement. And your hypotenuse is going to be square root of 2. Because remember, square root of 2 is what? 1.414. So it's just a slightly bit
It's
larger.
basically just like extra values that you can use because it's not
Exactly.
on 30, 60, 90.
Yeah, so you have the 30, 60, 90 degree triangle, and then you have the isosceles triangle to help you out. So anytime, like I said, you're working with these 30, 60 degrees, 45 degrees, and then of course your 0 and 90 degrees are going to be the most common angles. So once you get familiar with those sine, cosine values, you will actually be able to come up with your own unit circle also. Then you really wouldn't need to have one along with you, because then you can use the idea of reference angles and come up with all the values on your circle. So in this case, if we are talking about sine of negative 3 pi over 4 in terms of the reference angle, what would be negative 45 degrees in radians? Yeah. It would be negative pi over 4. So we're talking about sine, and it really doesn't matter which angle you use, you'll get the same thing. So what does this ratio come out to be? Opposite over hypotenuse? Yeah. Very nice. This is a third quadrant angle. So your value is going to be negative square root of 2 over 2. Now, if you actually think about that table I was talking about, cosine and sine values are the same, right? So it's actually going to be negative square root of 2 over 2. Because think about it, if I'm talking about 45 degree angle and we're going adjacent over hypotenuse, I'm still getting that same fraction of 1 over square root of 2, and you rationalize it again to get your value. Now what will our tangent function look like for this guy?
1, yeah, 1. Because it's just going to be root over 2 over root over 2, well, negative root 2 over 2 over negative root 2. So it's just the same.
Yeah, you're dividing by the same number, right? So since these are the exact same values, they basically cancel each other out. The two negatives will become positive, giving us 1 as the answer. And then what about the reciprocal functions? Cosecant, secant, cotangent.
This is just going to be root 2, negative root 2.
Yeah, because, ooh, I guess I should put a negative sign here. So again, you can do it from this guy, or just think about inverting 1 over square root of 2, which will also end up giving us, it will be the same for both. And what will that make our cotangent? Still be 1, right? Because you're, same thing, you're still dividing, inverting this, but dividing by the same numbers. And that will be a positive 1 for your tangent and cotangent. And I want to make sure I didn't miss any signs in this guy. Start with negative, positive for this guy. Okay, did you have any questions on part D? We're okay?
Yeah.
Alrighty, guys.